Calculus 2 video lecture number 12 on separable differential equations. So in the previous lesson, we went over what differential equations were and how to verify that certain equations were solutions to them. Now we're going to look at how to find solutions to a particular kind of differential equation, and that's a separable differential equation. Now, how do you know you have a separable differential equation? Well, it has to be first order, meaning y prime, the first derivative, is the highest order derivative you have in the equation. And the expression for dy dx can be factored as a function of x times a function of y. So in other words, it should have the following form. You should be able to write dy dx as some f of x times some g of y. And then in order to solve for y, to find the solution to the differential equation, you're going to isolate all the terms with x on one side of the equation, move the dx over there, and then put all the y terms on the other side, the dy over there with it. You're going to integrate both sides of the equation, and then if possible, try to isolate or solve for y. All right, so let's look at some examples. Example 1, solve the differential equation. We have dy dx is equal to rad x over e to the y. So the whole reason that these are called separable is because you're going to separate the differentials, dy and dx, from each other. And you're going to group all of the terms with y's wherever dy is, and all of the terms with x where dx is. And you can't have a differential in the denominator. So that means I'm going to keep dy on the left, and I'm going to multiply both sides by e to the y. So I have e to the y dy, and then that's going to equal rad x dx. So notice the differential dy matches up with all the terms that have y in them on one side. Dx has all the x terms with it. Okay, so everything's separated nicely. Now what I'm going to do is go ahead and integrate both sides of the equation. So just add an integral sign. Now, antiderivative of e to the y, that's just going to be e to the y plus c, yes, but when we solve differential equations of this form, we usually just put the plus c on one side, usually the right. So I'm going to save it for when I anti-differentiate the right-hand side now. So let's see here. This is x to the 1/2. If I add 1 to the exponent, it's going to become x to the 3/2. Divide by that new exponent, so it's 2/3 x to the 3/2, and then put the plus c here. All right, looks good. Now let's see, can we solve for y? Can I isolate it? Well, sure, let's take the natural log of both sides. So I have natural log of e to the y is equal to the natural log of 2/3 x to the 3/2 plus c. And then notice now on the left-hand side, I'm just left with y all by itself. And then I have natural log of 2/3 x to the 3/2 plus c. So notice here my solution is actually a family of equations that satisfies the differential equation because I have plus c plus this constant c. If I was given some sort of initial condition, then I could find a particular solution, but instead I have a family of solutions here. All right, hopefully that was straightforward enough. Let's look at a couple other scenarios. Example 2, solve the following differential equation. We have y prime equals y squared times sine x. So to start things off, since it's separable, I'm going to replace y prime with dy dx. And this is equal to y squared times sine x. Now, notice sometimes the trivial solution, just where your function is equal to 0, is going to be an option that won't emerge when you're solving by integrating, but it's something you want to observe and mention. And I'm noticing that that's the case here with this differential equation, because if y is equal to 0, obviously I would have 0 squared times sine of x equals its derivative. And that's not interesting, it's not very exciting, it's trivial because it's just a constant function. You're not solving for any function that's varying in an interesting sort of way, but you do want to mention it. Okay, so just be on the lookout in case it pops up. state that it's there. Also, y equals 0, the trivial solution satisfies this. Okay, fantastic. Now let's move on. So it's separable. I'm going to move y squared to the left-hand side. So it's actually going to be 1 over y squared dy equals sine of x times dx. Remember the differential, so dy and dx are not allowed to be in the denominator. No, no, no. Now we can go ahead, let's integrate both sides. So antiderivative of 1 over y squared, remember, that's y squared in the denominator, meaning y to the negative second. If I add 1 and divide by the new exponent, now it's negative 1 over y. And then antiderivative of positive sine x is negative cosine x. And then we have that plus c. Okay, good. So let's see, can we isolate y? Well, let's multiply through by a negative. So we'll have 1 over y equals cosine of x minus c. And then if I take the reciprocal of both sides of the equations, now I've isolated y. So y equals 1 over cosine of x minus c. So there's the solution there, along with y equals 0. Notice y equals 0 is not part of this family, right, of solutions that we have here. So make sure you do mention it, okay, because it's relevant. All right, these ones were pretty straightforward. We didn't do any fancy integrating. Let's visit something else that might be a little more spicy. So we've got dy dx equals e to the y sine squared x over y times secant of x. Okay, well, I know I want to keep all the terms with x on the right-hand side, all the terms with y on the left-hand side. So I'm going to have dy times y, and then if I divide by e to the y, that's the same as e to the negative y, right? So I have e to the negative y times y dy on that side, on the left-hand side, equals sine squared x over secant x dx. Okay, I'm going to clean this up a little bit. Let's write this as y times e to the negative y dy. And then if I have secant x in the denominator, that's the same as having cosine x in the numerator. And it's time to integrate both sides. Okay, so keep track of everything. This y is over here. Since this e to the y is in the denominator, now it's e to the negative y. And then I rewrote secant x in the denominator as cosine of x. All right, so let's see. How would we integrate the left-hand side? I have y times e to the negative y. So think back on your list of integration techniques. U-sub's not going to work. What's next on the list? That's right, it's by parts time. Oh my goodness. So we pick a u and we pick a dv. U should be y, right? And then dv is going to be e to the negative y dy. So then du is dy. V is going to be negative e to the negative y. And we're going to be left with negative y e to the negative y plus the integral of e to the negative y dy. And this is going to give us negative y e to the negative y minus e to the negative y. And then I'll just put a plus c1 just to show you if you wanted to put a constant, what you could do. Okay, what about the other side? Oh, it's u sub time, right? You're going to let u equal sine x. Then du is cosine x dx, the odd man out. So you basically are going to have the integral of u squared du, which becomes 1/3 u cubed plus c2. Let me plop that in right here. And then I'm going to replace u with, that's right, sine of x. So 1/3 sine cubed x plus c2. Okay, now in this case, it's not going to be nice to solve for y. So we'll just clean things up a wee bit. I can factor out, notice, this e to the negative y. Okay, so that's something. So let's take it out. And then I have negative y minus 1. Let's take out a negative with it. That way it's just y plus 1. Looks way cuter. And then we have 1/3 sine cubed x. And then I'm just going to put plus c, where this c is equal to c2 minus c1. Okay, so if you put a plus c on each side, make sure you distinguish between the two of them. And then at the end, if you're summarizing, you're clear about your constant. Or, just don't even put this, and then you can just write c on the right-hand side like I did in the previous problems. You've got options. Just make sure you're precise with whatever you choose to do. All right, how was that one? So yes, in solving differential equations, you're going to have to integrate and at times use those techniques that we covered before. That can be very fun. Okay, example 4. Now we're going to find the solution of the differential equation that satisfies the given initial condition. And in this case, the initial condition here is that y of 1 equals negative 1. Basically, we're going to use that to find c at the very end, to find that constant. So we'll hold off on that till later. First things first, I'm going to rewrite this equation. So I have x times dy dx plus y equals y squared. And right now you might be nervous. It doesn't look separable. So let's see. Let's divide through by x because I want to isolate dy dx, right? So I can make it separable. So I'm going to divide the whole equation through by x. Let's see what's going on. So I've got dy dx plus y over x equals y squared over x. And then if I subtract y over x, now I have y squared minus y all over x. Okay, can you see how this is separable now? Good. So I'm going to have 1 over y squared minus y dy equals, here we go, 1 over x dx. And now we can integrate. All right, how do we deal with the left-hand side? Why, yes, it's time for partial fractions. So let's do the decomposition. We have 1 over y squared minus y is y times y minus 1. So this equals a over y plus b over y minus 1. Multiplying through by the LCD, I get 1 equals ay minus a plus by. Okay, so I can see here a plus b has to equal 0, and also a is negative 1, which means b is 1. And so now I can integrate. I'm going to have integral of a is negative 1, so this is going to be negative 1 over y plus 1 over y minus 1. That is the left-hand side. Right-hand side is ready to go, but I'll just rewrite it the way it is so we can anti-differentiate all at the same step. Okay? Good. So first integral is going to be negative natural log absolute value of y plus natural log absolute value y minus 1. I'm going to save the plus c just for the right-hand side, okay? And then this equals natural log absolute value of x plus c. There's my c. Okay, can I solve for y? I sure can. So I'm going to use my logarithm properties and combine these two into a single logarithm. Think of it. The logarithms are being subtracted. So I could write this as natural log of y minus 1 over y, right? Equals natural log of x plus c. And then to get rid of the natural logs, I can take e and raise it to both sides of the equation. I can exponentiate both sides. So I have e to the ln of y minus 1 over y. Now be careful here, okay? You have e raised to the natural log of the absolute value of x plus c. You have to raise it to the entire right-hand side of the equation. Okay, the left-hand side's pretty straightforward. We have absolute value y minus 1 over y left over. Now you be careful here with your properties of logarithms and exponents. Because if you have e raised to a sum, if you split it up, you have to do so using multiplication. This is e raised to the ln, absolute value of x, times e to the c. Yes? We remember our rules of exponents? Fabulous. Now we have absolute value of y minus 1 over y equals, now e raised to the ln of the absolute value of x, that's just absolute value of x, times e to the c. You can't just have c, it has to be e to the c. Okay, now if we're going to drop the absolute value bars on both sides of the equation, that's fine. I just have to put plus or minus on one side. Let's put it on the right side, it'll look cleaner. So we've got y minus 1 over y equals plus or minus x times e to the c. So I'm going to let k, some constant, be plus or minus e to the c, because e raised to the c is just some general constant anyways, right? It's just never going to be 0. That's the thing to keep in mind, is that k will never be 0, since e raised to some power will never give you 0. But it could be positive or it could be negative. Okay, so I'm going to replace all of this now with just k to clean up how the equation's looking. So now we have y minus 1 over y equals k times x. All right, now we were asked to use an initial condition, were we not? So we were asked to find the solution that satisfies y of 1 equals negative 1. So now I'm going to substitute in 1 for x, negative 1 for y, into what we have so far. So I have here negative 1 minus 1 over negative 1 equals k times 1. And so let's see here, what do we have? Things are cleaning up nicely, are they not? We've got k is equal to positive 2. And so substituting all that back in, I have y minus 1 over y equals 2x. I can multiply through by y, so y minus 1 equals 2xy. Ooh, we can solve for y. Let's put y minus 2xy on the same side equals positive 1. From here, I can factor out the y, and I have 1 minus 2x equals 1. And at long last, here's our solution. Y equals 1 over 1 minus 2x. Voila. Okay, make sure along the way you're keeping track of the constants carefully though, you're justifying everything, and then later on if you study differential equations in more detail, you'll see the importance of being careful at a step like this, because you'll be asked to specify what sort of values the constant can take on when it still appears in your solution. So if you replace e to the c with k or something like that, make sure you remember that it won't be 0. Okay, that's for further down the road. I got one more example for you guys. How's it going so far? Do you like this section? I think it's pretty fun. Here we go. So find f of x, again, so solve the differential equation such that f prime of x equals f of x times 1 minus f of x, and f of 0 equals 1/2. Okay, I'm going to replace this with dy dx. So replace f prime of x with dy dx. I'm going to replace f of x with y, and then this is also 1 minus y. okay? Don't let them use other notation and trip you out. You know exactly what's going on, okay? Yes, you do. All right, let's see here. Is this guy separable? It better be. dy dx is y minus y squared. I don't see any x's. Shall we have a panic attack? No, it's going to be nice. So dy over y minus y squared is equal to 1 times dx. Don't you agree? Okay, so it's just actually an easier little integral for us to do on the right-hand side with respect to x. Any thoughts? How shall we go about anti-differentiating the left-hand side? You are correct. It is partial fraction time again. Who would have known they were so helpful? Okay, so we've got 1 over, factoring the denominator, it's y times 1 minus y equals a over y plus b over 1 minus y. So 1 equals a minus ay plus by. So I can see clearly, okay, a is equal to 1, b minus a is 0. So if a is 1, then that means b is 1 also. So now let's start anti-differentiating. We have integral, they're both 1, so we have 1 over y plus 1 over 1 minus y dy equals integral of dx. All right, so antiderivative of 1 over y, that's going to be natural log absolute value of y. And then be careful, if we integrate 1 over 1 minus y, you're going to pick up a negative, right? You don't have to do a u-sub, but if you did, then you would pick up that extra negative. So just throw it in here now. Minus ln absolute value 1 minus y equals, and then on the right-hand side, all we have is little dx by his lonesome. So you're anti-differentiating 1, it's just going to be x plus c. Okay. Now from here, it's very similar to the last example that we just did. So again, we're going to use our logarithm properties and combine these into a single logarithm. So we have ln of the absolute value of y over 1 minus y equals x plus c. And then, yes, I'm going to exponentiate both sides. So I'm going to take e raised to the ln of y over 1 minus y equals e raised to the x plus c. Lovely. So now on the left-hand side, all we have is absolute value y over 1 minus y. And then do you remember how we wrote up the right-hand side? When you have addition in that exponent, you rewrite it as e to the x times e to the c. What do we want to do from here? So we want to drop those absolute value bars, say bye-bye to them. So y over 1 minus y equals, now I need a plus or minus here. And I'm going to switch them around, right? E to the c first and then e to the x after. Okay, now I want to clean this up. So I'm going to let k equal plus or minus e to the c. And so I can rewrite my differential equation now as y over 1 minus y equals k e to the x. And then if I didn't have any initial condition and I didn't have to solve for k, then this is where I would specify where k is any real number besides 0 or something like that, okay? However, we have an initial condition. They told us f of 0 is 1/2, so I'm going to find the constant now. Figure out what k is. All right, so I'm going to plug in 1/2 for y, so 1/2 over 1 minus 1/2 equals k times e to the 0. Well, on the left-hand side, I just have 1/2 over 1/2, right? Equals k. So k is 1. Aw, how sweet. Okay, so 1 over 1 minus y equals 1 times e to the x. Can we solve for y? Why, yes, we can. Let's multiply by 1 minus y. So we have y equals, distribute, e to the x minus e to the x times y. And then remember, if you're solving for a variable and it's popping up in more than one place in the equation, you want to get all the terms that have that variable on the same side. So y plus e to the xy equals e to the x. Factor out that y now. That's why we moved all those terms over. And I have 1 plus e to the x left over equals e to the x. And now we're home free. So we've got our solution. Y equals e to the x over 1 plus e to the x. And we are done. Okay. So that is it for the lesson on separable differential equations. We're going to learn one other kind in this class in Calculus 2, but know that there's so many different kinds of differential equations which you can study in a lot more detail. I think they're really fun, so hopefully you enjoyed the lesson. Be sure to give this video a thumbs up. Subscribe if you haven't already. It really helps support my channel. And share this video with your classmates and anyone else that you think might enjoy it.